The best way to picture an atom is as a compact, dense nucleus encircled by buzzing, orbiting electrons. This image prompts the following query: how do electrons continue to spin around the nucleus without ever slowing down? This was a big question at the start of the 20th century, and the search for an answer led to the creation of quantum mechanics. After countless experiments, physicists were just starting to piece together a coherent picture of the atom in the early 20th century. They came to understand that each atom was composed of a tiny, negatively charged cloud of electrons surrounding a dense, heavy, positively charged nucleus. They then proceeded to build a more thorough model with that broad picture in mind. The solar system, which has a dense nucleus surrounded by a cloud of smaller particles, served as the model's initial source of inspiration. However, this model introduced two serious issues. One is that an accelerating charged particle produces electromagnetic radiation. Also, since charged particles accelerate during their orbits, radiation should be produced by electrons because they are charged particles. According to researchers at the University of Tennessee at Knoxville, this emission would cause the electrons to rapidly spiral in and collide with the nucleus as they lose energy. In the early 1900s, physicists predicted that such an inward spiral would occur in less than a picosecond, or 1/1,000,000,000 of a second. This was not going to work because atoms obviously have longer lives than a picosecond. The nature of the radiation was a second, more subtle problem. Atoms are known to emit radiation, but it is known that the frequencies at which they do so are very distinct. If this model of the solar system were true, an electron in orbit would give off a wide range of wavelengths, which is not what scientists have seen. Famed Niels Bohr, a Danish physicist, was the first to suggest a fix for this problem. He proposed in 1913 that electrons in an atom couldn't just choose any orbit. The Nobel Prize citation entry for his subsequent award states that they had to be locked into orbits at very precise distances from the nucleus instead. He also suggested a minimum distance an electron could travel before it could no longer move away from the nucleus. These concepts didn't just appear to him out of nowhere. According to the hyperphysics reference page at Georgia State University, the German physicist Max Planck had suggested that the emission of radiation might be quantized, which would mean that an object could only absorb or emit radiation in discrete chunks and not have any value it wanted. However, the smallest size of these distinct units was a fixed quantity that became known as Planck's constant. Scientists used to think that these emissions happened all the time, which would mean that particles could give off radiation at any frequency. The units for Planck's constant are the same as those for angular momentum, or the momentum of a circle-moving object. Bohr then applied this concept to electrons orbiting a nucleus, claiming that the tiniest orbit an electron would have an angular momentum equal to 1 Planck constant. Higher orbits may have a Planck constant value of 2, 3, or any other integer multiple, but never a fraction of it. To fully comprehend why electrons have such a small minimum orbit and clearly defined higher orbits, quantum mechanics must be fully developed. Like all elements of matter, electrons exhibit both wave and particle behavior. One way to think of an electron is as a tiny planet that goes around the nucleus. Another way is as a wave that goes around the nucleus. In a small area, waves must abide by specific laws. They must be made of standing waves that can fit within the space, they cannot have any wavelength. Similar to when someone plays a musical instrument, only specific wavelengths will fit if the ends of a guitar string are pinched down, giving you the distinct notes. Similar to how an electron wave around a nucleus must fit, the first standing wave of an electron indicates its closest orbit to the nucleus. This image would continue to be improved by quantum mechanical developments in the future, but the fundamental idea remains: because of its inherent quantum mechanical properties, an electron can never be any closer to a nucleus. However, there is a completely different approach to the problem that makes no use of quantum mechanics at all. Just consider the various energies at play. An electron in an orbit around a nucleus is electrically drawn to the nucleus and is constantly being drawn in that direction. However, the electron also has kinetic energy, which propels it into flight. These two balance each other for a stable atom. Actually, an electron's total energy, which combines its kinetic and potential energies, is negative. This means that if you want to remove the electron from the atom, you must give it more energy. The planets in orbit around the Sun are in a similar situation. In order to remove one from the solar system, additional energy would need to be added to the system. Consider an electron falling toward a nucleus because of the attraction of its opposing electric charge. but it will never get to the nucleus because of the laws of quantum mechanics. Due to its orbital impasse, it becomes stuck. But since the system's total energy is negative, it is stable and stays together to make an atom that lasts, so physics lets this happen.